right, good morning, everybody. Thank you for those of you that have already worked through the first module. And check-in this morning, this is Thursday morning. About half of you have done the Delta Math assignment, and about 5 of you have done your quiz. So I'm going to go through and kind of batch grade those quizzes here soon. Everything for this unit, so you've just got the first part of 4. This is your second part of 4. It's going to be due next Friday, April 3rd. If stuff comes up, if you're having issues, please make sure that you're communicating with me, and some of you have done that. But just let me know what's going on. Just don't disappear from me, okay? All right, so let's talk about exponential growth. We talked about exponent rules last time. We talked about bases. We talked about our exponents, how to combine them, and things like that. So now what we're going to talk about is exponential growth. So you've done linear growth, or we've done linear growth a bunch, and if something's growing linearly, what we're doing is we are adding the same number every time. And so for exponential, instead of adding something every time, we're going to be multiplying the same amount every time. And that's the difference between the two growths, which is all over the news right now. The virus growth rate, that's what they're talking about, how the numbers are going up exponentially. We're going to look at an example using some recent data from the coronavirus. I'll let you know when we're about to start it. So if you don't want to listen to it, you can skip that part. I will have also put that time code in the notes. So if that's a little too raw for you right now and you don't need to listen to that, you can skip that example. That's fine. All right, so before we jump into that, let's just kind of talk about what this looks like. So here's a basic example. So say when you were born, your parents put $64 into a savings account for your college education and agreed to put money into your account on your birthday every year. They decided to increase the amount of their deposit by 50% each year. Complete the table showing the amount of your parents' deposit for 5 years. How much will they deposit on your 10th birthday? And then if we wanted to find out how much would have been deposited on your 21st birthday, what should we do? All right, so let's go ahead and talk about this for a second. So they said they're going to increase your amount by 50%. So that means they're still giving you the original amount plus 50%. So what they're actually doing is they're multiplying their original amount by 1.5. And so that's what we need to do to go through. So calculator wise, you can use Desmos for this. So Desmos has, the graphing calculator that we're used to, and you are welcome to type it in there. That works. They also have a for function and a scientific calculator if you would just rather not have all the bells and whistles. And so for this one, we're multiplying by 1.5. And so we get 96 for the first one. And then we're going to take our answer and multiply it by 1.5. And we're just going to keep doing that. So they asked us for the 5th, so that's your 3rd birthday. This is your 4th birthday, and then this is your 5th birthday. So 486 is what we're looking for. All right, so jumping back to those notes, let's go ahead and fill in that table. So this is 96, 144, 216, 324, and 486. All right, so that's part A, is filling that in. Part B is asking how much will your parents deposit on your 10th birthday? Well, we know year 5, so we just need to keep going. So jumping back over here, this is year 6, year 7, year 8, year 9, and year 10. Okay, since we're talking money, we want to make sure that we're rounding it to 2 decimal places. If that's how much money has, we only go to 2. We only go to a pennies place. So that ends up being $3,690.56. All right, so letter C says if we wanted to, not go ahead and find it, because I don't want to multiply that many times. All right, it says if we wanted to find out how much would have been deposited on your 21st birthday, what should we do? Well, we would need to keep multiplying another 11 times. But there's got to be a better way than that, and there is. There's an equation we can use to figure this out. All right, so the way to figure that out is a exponential growth formula. And there's two. There's one that's kind of basic, and then one that works if you have a percent. So for the basic one, it's y equals a times b to the t. Sometimes you'll see that as y equals a times b to the x. It's interchangeable. You can do it either way. So y would be your final amount. A is your starting amount. B is your growth factor. And T is time. And that is usually in years. Every once in a while it's not, but most of the time it's in years. So for that problem that we were just doing, our parents gave us $64 in our account to start with. And then each time we were multiplying by 1.5. And then T was our number of years. So to answer that last question, all we would have to do is substitute in 21 for T, mash the buttons in our calculator, and it would tell us how much they were depositing on our 21st birthday. So that's a much shorter way of finding that than sitting there and mashing the times 1.5, like 21 times if we were starting from there. Now, originally, they gave us that information as a percent, and there's a different formula that still ends up being the exact same thing that you can do using percent. So it's y equals a times 1 plus r to the power of t. All right, y is still your final amount. A is still your starting amount. T is still time. The only thing that's changed now is our r. That is our growth rate. And the one thing that you have to watch out for is you have to write that r as a decimal. So they're going to give it to you as a percent, and you have to write it in decimal form before you plug it into the equation. So for example, if I had 80%, I would plug in 0.80. If I had 5%, I would plug in 0.05. All right, so just be careful with that you want to make sure that you're writing it in decimal form when you plug it in. All right, so this next one is our coronavirus example. So if you don't want to see that, check my post with this video, and I'll tell you what time code to skip to. For the rest of us, this is what an exponential growth graph looks like. It starts out small, and then as the multiplication starts taking effect, it gets steeper and steeper and steeper. And so what this graph was, there's a link there for my data if you want to go check out the rest of it. But this is the number of confirmed cases on Tuesday nights going back to January 14th. And so graphing that out, you can see in the last week how there's been a huge jump. We're going right along here. This is the change from last Tuesday to 2 days ago. Is that big a jump. That's how much the cases increased. Now those are confirmed cases, so that's not death or anything like that. And one thing I will throw out there is we know that in the last week and a half or so, a ton more people have finally been able to get tested. So part of this a real explosion here, these cases were around, we just weren't able to test them. And so now it looks like it's growing much quicker than it did before. And this is the equation for that graph. And it's a little fuzzy. So it's a model. We've talked about this before when we've done linear regressions and quadratic regressions. It's an estimate. It's not perfect. This is saying that we started out with 0.00001 people having the disease. That's not a possibility, but just throwing that out there. And then this is saying that our growth factor is about 9. We know that's not true. The growth factor for this disease is about 3, which means if one person is sick, they're on average going to give it to 3 more people. So this growth rate is much higher because we're taking into account that there are more tests coming online. So it's not truly accurate. The graph is accurate. Those are the right data points that we have. However, there were probably more cases through this section right here that we just didn't know about, and so they weren't reflected in our total counts. I think down the road, when we go back and take a look at this, this is going to be kind of a case study for epidemiologists and virologists. They're going to definitely go back and be looking at the spread and be able to nail it down. And this is also countrywide. This would look much different if we were looking at North Carolina versus Louisiana, because there's a big outbreak right now in New Orleans from Mardi Gras is what they think happened. A bunch of people were together at the parades during Mardi Gras and then have now spread it. So there's a big explosion there. Versus North Carolina, it's still relatively small. I mean, we're going into shelter-in-place orders in a lot of places in North Carolina now, but that's because we're going to try and keep it small and shut it down. Like in Winston, I think we have 3 cases of community spread. That's more than enough. We don't need to have any more than that, so that's why they're trying to shut it down and keep everybody home and ride out these 14 days and then see what happens. So that's just a little bit of real-world data. You are probably seeing a different graph if you're looking online. If you're not looking online, you haven't seen this. But if you're looking online, you might be seeing graphs that look like this. And it's a bunch of different countries' rates and looks like that. So the difference is they're using a log scale. And we're actually going to talk about logarithms in our, not next week, but the week after. And it's the same type of scale that's used with earthquakes, with the Richter scale. And so we'll get into what that looks like. But this graph right here over on the left, that's got a linear scale. So this is 50,000. So each of those boxes is 10,000. So that's 10,000 cases, 20,000 cases, 30,000, and so on. Versus the log scale might be 10, then 100, then 1,000, and so on. So we'll look, when we get to logs, we'll look at one of those graphs in a little more detail. Okay, that's enough coronavirus stuff. That being said, you guys know if you have questions and just like random stuff that's not about math and you just want to ask, shoot me an email. I got you. All right, example 2. So we're going to write an equation for this, and then we're going to graph it and use the graph to help us make some predictions. All right, so it says in 2000, the U.S. population was 281 million, and the annual population growth rate was 1.24%. Write a function for the U.S. population as a function of a number of years since 2000. All right, so x is going to be number of years since 2000. And y is going to be the U.S. population. And one thing we want to include in that is that it's in millions. Okay, so that 281 is our starting amount. That's our R, so we need to turn that into a decimal form. So it's 1.24%. To turn it to a decimal, you're taking that decimal place and you're moving it 2 places to the left. So we're going to end up with 0.0124 as our R when we plug that into the formula. So it's going to be y equals 281, because that's our starting amount, times 1 plus 0.0124, and then there's our x. You could also use t. I'm using x because that's what they specified in the problem. Now for this one, you can leave it like this. That is completely fine, and you can go ahead and work as is. You can make it a little shorter, especially if you're typing things in the calculator, by just going ahead and doing the addition, which is super easy because you're just adding 1 to your decimal, so it's not like it's super stressful there. So you can do that and use a slightly simplified version. That works as well. All right, so it says use the function to predict the U.S. population in 2015. So we started in 2000. So that means 2015, our x is going to have to be 15. If you put in 2015, what you're saying is, what's the population in the year 4015? That's not what we want. So we want to plug in 15 for our x. And you can do this in whatever form of calculator you like. I think for most of you, you would probably be reaching for this Desmos, but it works for either one. All right, so we're going to have, sorry, it's a little funkier with the tablet. So we're going to plug in 281 times 1.0124. And then we're going to the 15th power. And so that gives us 338 roughly 1 million people. So it's saying in 15 years our U.S. population grew by quite a bit. Oops. I just drew that in the wrong spot. All right, we're just going to draw some arrows and roll with it. Sorry about that, y'all. Okay, so that part goes right here. All right, so the second part for letter C, it's saying use the function to predict when the U.S. population will reach 350 million. So that would be looking at this and trying to figure out what x is. Right now, we don't know how to do that mathematically. You will in like 3 weeks, but right now we're not there. So what we're going to do is we're going to let Desmos help us out. So we're going to come back over here. We're going to type in our equation. All right, so there's our graph. We want to look at this, so I'm going to zoom out just a bit so we can actually see the thing. There we go. And it was asking for the when the U.S. population reaches 350 million. So I'm going to type in y equals 350 and look for the point where they intersect, and that's our answer. So it's right there. So 350 is our population, so the 17.8 is our number of years. That means 17.8 years after the year 2000. So translating that, that's going to be about somewhere in the middle of the year 2017. All right, let's do another example like that just to make sure we've got it. So in this one in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. Write an exponential growth model giving the number of incidents T years after 1996. All right, so T is years after 96. N is the number of incidents. All right, so it's going to be N equals. Our starting amount was that 2,573 computer viruses. All right, and it's increasing by that rate. So if that's 92%, that's going to become 0.92 when we plug that in. All right, so there's our equation. All right, so the next one, they're asking us to sketch it. So when we say sketch, remember, that's not perfect. That's just getting the rough idea of what that would look like. All right, so we have 2,573 times 1.92. I'm just going to go ahead and do the addition there. and then we've got to the power of x. All right, I'm going to adjust my window just as a reminder that this is the thing. If you click on the wrench right here, and then you go to your x-axis and your y-axis, you can adjust those. So for this one, I'm going to make it 0 to 10. And then we know it's 2,573 to start, and then it's going up. So I'm going to make it like 0 to 25, or 250,000. Oops, come back here. All right, cool. And then you tap the wrench and it's gone. All right, so there we go. We've got a pretty good idea of what our graph should look like. When you're sketching it, loosely label the axes so you know what you're talking about, like as a scale, but it does not have to be perfect. All right, so that would be roughly like that. All right, and then part C says use the graph to estimate the year when there were about 125,000 computer security incidents. All right, so I'm jumping back to Desmos again and let it do the work for us. So y equals 125,000. There we go. Tap your button. It's going to let us know. So about 5.95 years. So almost 6 years. So jumping back over here, we started in 1996. So that's going to be, so we're adding almost 6 years. So it's right at the tail end of 2001, 2002. All right, so that gives you some ideas of what these graphs look like for exponential growth and how to write your equations. Now, where these get used in the real world. Now, that being said, we did definitely use virus spread. That is an exponential growth. But this really comes up in banking. This is where you're going to see it the most. And you won't really generally ever have to do these calculations on your own. But if you go and read the fine print for credit cards you may get, bank loans you may get, this stuff is in there. So if you understand the terminology now, it's going to make things easier for you as an adult. You're not going to be like, whatever, I'm just signing this and it'll be fine. That way you won't get taken advantage of. All right, so compound interest. What happens is with banks, they look at how much money is in your account, and then depending on how often it's compounded, they'll give you an interest payment. They'll add a bit to your account. Usually that's with savings accounts. Sometimes if you've got a really good bank, they'll do it with your checking account too. Most of the time though, it's savings accounts. All right, so this is what the formula would look like for this. It's still an exponential growth. It's just a special case of it. So if you look at that, that still looks real familiar. I mean, it still looks like the percent formula that we talked about earlier. All right, so A is your final amount. P is your starting amount. But when we're dealing with money like this, it has a special name. It's called your principal. All right, if you look, you see N in 2 places in your formula, and that's correct. It's in both places. And N is the number of times it's compounded per year. All right, we already know what T is. It's time. And we already know what R is. It's your interest, your growth rate. All right, so before we actually work some of these, let's talk about the different ways your interest can be compounded. All right, so your bank could compound it daily. And so if their n is the number of times it's compounded per year, if they're compounding it daily, that would be 365 because there's 365 days. All right, they could compound it weekly. And if it's weekly, it's 52 days. Not 52 days, sorry, 52 times. All right, if it's monthly, that would be 12 because there's 12 months in a year. If they did it bi-monthly, that means every 2 months. So that would be 6 of those in a year. They could do it quarterly, which would be 4. Semi-annually means twice a year. So that would be 2. Or lastly, they could do it annually. That is not how you spell that word, sorry. And that would be once a year. All right, so for these, it makes sense if you stop and think about it. That's not necessarily something I need you to memorize. If you just think, you should be good to go. That being said, your quizzes are open notes. If you write this down, you've got it, so you should be okay. All right, so for example 4, I said you deposit $4,000 in an account that pays 2.92% interest. Find the balance after 1 year if the interest is compounded quarterly or if the interest is compounded daily. All right, so let's go ahead and write our equation. So we're going to be starting with $4,000. And then our interest rate is 2.92. So we still need to move that decimal. So that would be 0.0292. And in part A, it's being compounded quarterly. All right, checking over here on our table, we said if something's compounded quarterly, that's 4 times a year. We also need that 4 right there. And then it's after 1 year, so it's 4 times 1. All right, from here, just type it straight in Desmos or your graphing calculator. If you're using the TI and you have an older operating system, just be a little careful with that. They're not great with fractions. So be real careful. You may want to do a step at a time to make sure you've got it all in there. If you're using the newer operating system where you can hit second division and pull up the fraction, then you should be good to go. And then for Desmos, it's fine as well. So clearing that out, typing that in, we've got 4,000 times 1 plus 0.0292. Oops, my 0 didn't show up there. 0.0292 divided by 4, because we're doing this quarterly. All right, and I would just go ahead and do the multiplication first before you type it in. 4 times 1, it's 4. I think we got it. All right, so there we go. It gives us $4,118, and we want to, since it's money, we want to go to 2 decimal places, so 9 cents, 0.09. So that doesn't seem like a whole heck of a lot. On the other hand, just leaving your money in the bank account, not doing anything else to it, you made almost $120 for not doing anything, just leaving it in the bank account. So that's the power where interest can come in. It can be helpful like that. All right, so let's look at it if it's daily. So the formula is going to be exactly the same, except our n is going to change. So it's still 4,000 plus 0.0292. But if it's compounded daily, that's 365. All right, so same thing. Let's jump back to Desmos. All we need to do is change those two n's. So that one needs to be 365, and that one needs to be 365. And our answer is pretty similar. It's still $418. It's just $418.52 now. So that doesn't seem like that big a difference. And, it's not. It's, 40 some cents. But if you're dealing with bigger amounts of money, that can have a bigger effect. So it's just something to be aware of. Okay, so those are two different examples of doing compound interest. I've got one more thing I want to show you. And E. So this is also called Euler's number, which is kind of bizarre because it doesn't look like that's how you would pronounce Euler, but it is. And what it is it's a number like pi that goes on forever and ever and ever. So just like we round pi to 3.14, we round e to 2.718. And there is an e button on your calculator. Desmos recognizes it if you type it in as lowercase e. If you're looking for e on the TIs, it's on the left-hand side. And if you're using just your regular phone calculator, if you turn it on its side, you're going to get e as well. It'll pop. It's one of the big ones that pops up over there. All right, and so this is what the graph of e to the x looks like. It's still exponential growth. It's just with a specific base. Your base is 2.718 as opposed to like 2 to the x power or 3 to the x power. It's that specific number. And so e takes place in a formula for continuously compounding interest. All right, so I'm going to date myself here for a second. When I first started teaching this, I would be able to just say, hey guys, it's the shampoo formula, and everybody would know what I was talking about. Not everybody uses Pert Plus anymore, but it was a really popular shampoo back when I first started teaching, back in the dark ages. So if you have heard of that, that maybe is one way to remember the formula. It's just the shampoo formula. But A is still your final amount. P is still your starting amount, your principal. All right, E is just E. You're going to use the E button on your calculator. Don't do anything else to it. You're not substituting it in. It's not a variable or anything like that. It's just a number. And then R is still our percent. Turn to a decimal. And T is still time. All right, so most of this, it's just using a different number. Otherwise, it's exactly the same. So when we were doing, on the last example, we talked about the different types of ends. There was daily, there was weekly, there was monthly. So in theory, you could do hourly, you could do minutes, you could even do every second. This one is compounding continuously. So it is every possible time your account is being compounded, and they would give you the extra money. And continuously compounding is when you're going to get the most money from your bank account. So if you happen to find a savings account that compounds continuously, jump on that because you're going to make a whole lot more money than anything else. All right, so for example 5, we deposit $5,000 in an account that pays 6% annual interest compounded continuously. What is the balance after 1 year and after 5 years? All right, so if we're going to do 1 year, that would be y equals 5,000 because that's our starting amount, E. And then our interest is 6%, so 0.06, and then 1 year. So that would be T. All right, for 5 years, same formula, y equals 5,000, E to the 0.06, but instead of times 1, it'll be times 5. One thing to watch out for is how to know which formulas to use. They have to tell you in the problem. They have to say compounded monthly. They have to say compounded yearly, or they have to say compounded continuously. So your job is to read the word problem and figure out which one they're talking about. All right, I'm going to jump over to Desmos real quick and solve these last couple. All right, so we got 5,000 E, and on Desmos, you just need to type in the E. Just hit the E on the keyboard. Again, if you're using a TI, go ahead and look for it over on the left-hand side. And then we need this to go back to exponents. And then we have 0.06 times 1, so I'm just going to leave it as 0.06. You can, if you want to put it all up in there, I'll show you in a second. we'll do it for in parentheses. All right, so this is saying after 1 year, if you put $5,000 in that account and it's compounded in, continuously, you're going to end up making almost $310 for doing nothing. It's just going to sit in your account and it's going to compound. All right, so let's try and see what it would be for 5 years. So we've got our E. For our exponent, we'll put parentheses. So we have 0.06 times 5. And there we go. So after 5 years, not doing anything, the bank's going to end up giving us $1,700 and almost $50 in interest, which is pretty sweet. So again, that's why I said if you find a bank account that compounds continuously, jump on that. Oops. All right, so let's go ahead and record our answers. So we had $5,309.18. Remember, it's money, so we always want to go 2 decimal places. And then for 5 years, we had $6,749.29. All right, so we have basically in these notes covered all the possible types of exponential growth that you could see. So I'm going to set up another delta math for you guys to work on. And then we'll have another quiz that goes with it, just like we did for exponent rules. All right, let me clarify this because I had a couple of you that got stressed out, and I just want to make sure we're all good on this. All right, so first off, you have until next Friday to complete this. So do not spend 2 hours beating your head against the wall with delta math. If you get stuck, send me a message. Either ask me a question, like, take a picture of the problem, say, hey, I'm getting lost, what's going on here? And can we go back over this a little bit? Or say, hey, Ms. G, I really just need to talk through some of these with you. Can we set up a Zoom? And we can set up a Zoom and I can share my screen and we can do some of those delta math problems together. So I am totally fine doing that as well. But you've got to reach out and let me know that you need that help. All right. So we have a Zoom this afternoon for those of you that are listening to this on Thursday. I only scheduled 1 for this first week. If you guys think you need 2 next week for office hours, let me know, and we'll today during our Zoom, or shoot me an email and let me know, and I can set up more than 1. We can make 2 if we need to. All right, sounds good. Have a good rest of the day, and hopefully I'll see some of you this afternoon.